Well, hi there, folks. My name is Cyrus Bruzy, and I am a computer vision developer, and I lead the SDK team over at TrueFace, which is a AI and computer vision company specializing in face recognition software. As part of my job, I have to work with machine learning inference frameworks to write high-performance inference code in C++ for both CPU and GPU, so I commonly work with ONNX runtime as well as TensorRT. And about a year ago or a year or two ago, I created this open source repository called TensorRT C API, and it had an overwhelmingly good response, and a lot of people were interested in learning more about TensorRT and the C API. So I decided that today I'd make a follow-up video just diving into some of the code in this repository, just to shine some light on how a few things work, just because TensorRT can be a little bit of a confusing framework. So essentially the way today's video is going to work is that I'll open the code in a code editor. Right now I'm using CLine as my code editor of choice, and then I'll essentially walk through the code and hopefully provide some insight on how things work. So just to give an overview of the project structure one more time in case you haven't seen the project in a while, it's pretty simple. It just contains three source files, our header, our main CPP, and of course our entry point main. We also use Cmake in order to compile, link everything, take care of all our files. So we'll just start by looking at the Cmake file here. It's a pretty standard Cmake where we are creating a library from our CPP file, and then we're creating an executable which links against the library that we created called TensorRT C API. And the one caveat that you need to ensure is that in the repository, I've included the Cmake directory here, and within it there is a find TensorRT Cmake, which you need because TensorRT does not provide their own for some reason. So just make sure you copy this into your project as well. You can just copy paste it, and then in your Cmake there's two things you need to do. So you just need to set the Cmake module path to the directory which contains this find TensorRT Cmake. So in our case, it's going to be the Cmake directory specified here. And then from there, we need to also set the TensorRT directory based on where we've installed TensorRT 2 on our devices. And there's instructions on how to do this in the Git repo. And then finally, we can just call the find package TensorRT call. And then from there, it should be populated within this variable here. So the Cmake file is relatively straightforward, so we can then dive into the main file. So what we do in our main file here is that we start off by defining our configuration options. So we've defined this structure called options, which I'm going to jump into here. It's defined in our engine.h header file. And basically what the options contains is various options that can allow us to dictate how we want the TensorRT engine to build the model file. So things like the precision to be used. Do we want to use 32-bit floating point values or 16-bit floating point values? They're generally both as accurate. I mean, obviously 32-bit is going to be more accurate, but 16-bit is almost as accurate, but it can be twice as fast. So I generally do advise using 16-bit floating point values. We have the opt batch size, which is going to be the optimal batch size that we want to use. So, if in our application we expect to consistently be using a batch size of 1, then we want to set this to 1. If it's consistently going to be 4, then we set this to 4 or whatnot, just because when we generate the engine file, we're going to optimize for what this value is set to. And then we have our maximum batch size, which is the maximum batch size we expect to see. And if we try and provide a batch size larger than the specified max, TensorRT will actually complain. So be sure to choose that carefully. And then we have the max workspace size, which, I would just try and max that out. Basically, it's the GPU memory which can be used while TensorRT tries to run through the various optimization profiles to fully optimize the model. So we want to be relatively generous with our allocation there. And then finally, the device index. So, if you only have one GPU, you want to leave this at 0, but some people with fancier setups might have a multi-GPU device, and you can therefore specify which GPU you want memory to be allocated on, you want inference to be run on, and so on. So let's go back to our main file now. So in this example here, we create an instance of this struct, and then one thing that I forgot to mention is that we also have this field called does support dynamic batch size. So when you're exporting your ONNX model, you have two options essentially. You have the option to choose a static batch size. So, I want a batch size of 1, 4, 16, whatnot. Or you can set it as a dynamic batch size where, in code, it'll probably be set as a variable. So, like a string, or it could be set to -1. And I generally advise models with dynamic batch sizes because that allows us to use dynamic batch sizes at runtime, which is a very powerful tool. But sometimes the model you're working on has been pre-exported, like the ArcFace model we have here, and it's been done with a static batch size. So be sure to set this variable appropriately. And then here we just set a few configurations options. As you can see, if the model does not support dynamic batch size, we set the opt and the max batch size to 1 here. And then essentially we are constructing an instance of the engine class. So let's go into the engine class to see what the constructor is. As you can see, we're passing the options there. So I'm going to jump into this. Here's the engine class constructor. So not a whole lot being done. We're just setting some member variables here and setting a warning. If you specified that it's a static batch size only, then just FYI, the opt batch size and the max batch size are going to be changed to 1 by the implementation. So let's go back here. Oh, sorry, wrong file. Let's go back here. So now we're going to specify our ONNX model. So in this example here, we're going to be using the ArcFace ResNet 100 model. This particular model is a face recognition model which works on face chips. So the input has a static batch size of 1 and 3 channels, and then the height and width are 112 by 112. So the total dimensions are 1 by 3 by 112 by 112. And if you want to know where to download this from, you can actually just go to the repository, and I do have a link here in the sanity check. You can download it here. So next we're going to actually build the engine file. So what this does is essentially we take this ONNX model and then we generate a TensorRT engine file from it. So let's go into this build function to see what exactly is happening here. So now we're in the build function here. So the first thing we're going to do is we're going to call this serialized engine options method, where we pass the options to it. So these are the configuration options for the TRT model. And basically what this method does is it serializes these options into a string. Okay, and the reason we do this is that we are actually going to use this serialized string, serialized model name with all the options, as the model name when we write the TensorRT file to disk. And the reason we do this is because essentially we want to avoid regenerating the TensorRT engine file, as it's a pretty slow process. So basically we're going to generate it once and then save the engine file with the name of all the configuration options. And then the second time we run it, essentially the application can say, hey, does this already exist on disk? And if so, we can just read it on disk and bypass the building engine phase. However, if any of the configuration options have been changed, then we do need to rebuild it, which is why we serialize it into the name, because then the name will be different from the model we previously saved onto disk, and then that'll invoke a rebuild. So just so you know why we serialize it there. So essentially we serialize it and then we check, hey, does this file exist? And if the file does exist, then we can just immediately return, because we don't need to regenerate that TensorRT engine files for that specific configuration options. But if it does not exist, then we actually need to build it, okay? So to build it, this is just some TensorRT boilerplate, and then we set the max batch size based on the provided max batch size that was specified in the configuration options. And then we need to specify a explicit batch size. And the reason for this is that implicit batch size is now deprecated. And you can read more on that subject, at this link here. Next, we create a parser, and this parser is going to read the ONNX file. So generally, you can actually parse a ONNX file directly from disk just by providing the name of the ONNX file. However, in our case, we're just going to read it into a buffer first. So, we have a character buffer here, which is just a vector of characters. And the reason we do this first is, to accommodate for the in case of, let's say your model file, like we do at TrueFace, had been encrypted, then you can read it from disk into a buffer decrypt this buffer, and then from there parse the buffer which is already in memory. So that's what we're doing here. Just gonna have some water here. Next, we get a config, and this is going to allow us to set some further configuration for the TensorRT engine file. So the first thing we're going to do is register an optimization profile. You can actually register as many optimization profiles as you choose, but in this demonstration, we only register a single optimization profile. And the one thing to note is that we need to register that optimization profile for all the inputs, okay? This code works for models which not only have single inputs, but that can have multiple inputs. And that's why here we're getting the number of inputs, and then we iterate over each input, obtaining the input name and dimensions, and then we specify the min batch size, optimal batch size, and max batch size for that input. Okay, so if we have one input, this loop's just going to run once. If we have 10, it's going to run 10 times, once for each of the inputs, until we specify the profile for each one of the inputs. And only after we've done that can we register the profile. So initially I had a bug where I had this piece of code in here, and that was causing tons of issues because I was basically registering a profile that didn't have the profiles of all the inputs specified, only for, you know, the current iteration of the loop, and that was causing me lots of troubles. So just make sure that's on the outside there. And then here we set the max workspace size, we set the precision, pretty straightforward stuff. Now here we are creating a CUDA stream, which we're going to be using for some of our asynchronous operations here, primarily in this case building the network. So basically we create the CUDA stream. I've defined this function here, check CUDA error code, which anytime I call a CUDA method, I wrap it in this, and basically what this method does, it's pretty straightforward. It just checks the code, and if it's not equal to 0, it essentially just converts the code to a string and gets the appropriate error name. Just the little verbosity error checking, you know, always good to have. So let's go back here. Basically we set the stream for the config, and then we build our network. And, you know, hopefully the build works. If the build does not work, it's going to fail here. And once it works, then we basically write the TensorRT engine file to disk using the engine name. So this engine name is basically the serialized name that we serialized earlier. And what should you do if your engine file, the build phase of your engine file fails? Well, what I suggest to do, what I mentioned in the documentation here too, is I suggest use the TRT exec command line tool. It comes packaged with the TensorRT download in the bin directory. It's a very powerful tool, gives you tons of verbosity. You can also choose to actually up the verbosity here. I forgot what verbosity level we've set the logger to here. We've set our logger to just warning level. You know, you can set this to, I forgot what the severity levels are. Let's see. You could set this to verbose as well. You know, like if you go here, you could set this to verbose, and then that'll spit out more information too. But I personally like the command line tool for debugging, you know, as we don't have to like recompile our code and do all that stuff. So perfect. Now we can go back to our main file because we've just finished the build method. Now if we go down, the next thing we call is the load network method. So just remember, if the engine file has already been built and is already saved to disk, then essentially the subsequent time we call or run our program, it's not going to rebuild it. It's just going to go straight to the load network method. So basically here, you know, we're just reading the serialized model from disk into a buffer. And then here, since we're going to start allocating GPU memory relatively soon, we need to set the CUDA device. So this basically tells CUDA, hey, on all the subsequent, you know, memory allocations, CUDA operations, which device should these be performed on. So we need to make sure to specify that it's the one we plan on running inference on. Okay, and we have a little error checking in case you try and set the device index to a device index that doesn't exist. It's not going to be happy, of course. Here we just have some more boilerplate TensorRT code. And then this is where things start to get interesting. So we have this member variable called mbuffers. So let's go to the definition here. Mbuffers is a vector of void pointers, okay? And the reason we need this is if we actually go down to the enqueue call. So this is where we actually run TensorRT Inference. I just jumped here to just show you the API, so I'm going to jump into this definition here. We see that enqueue-v2 takes this variable called bindings, which is an array of pointers to the inputs and output buffers, which are GPU memory buffers, which the caller needs to allocate, okay? And that's basically what we're going to do right now. So let's go back here. Okay, so we're going to basically resize this array of void pointers to the number of bindings. So this NB bindings, this refers to both inputs and outputs. So in our arc-face model, this is going to return 2 because we just have one input, one output. But in different implementations, you could have multiple inputs, multiple outputs. So this will account for all of them. And then we just create our CUDA stream because basically what we're going to do is we're going to allocate memory asynchronously. And then right at the end, we will synchronize our CUDA streams and destroy them. And that just allows things, speeds things up a little faster because, we can do asynchronous operations there and have other CPU logic while this GPU logic is executing here. So essentially what we're going to do is we're now going to iterate over the bindings we have. So this is all the inputs and the outputs. And then basically we're going to say, we're going to ask the engine, is the binding at this input index, is it an input or an output? And if it's an input, we're going to go in this piece of logic. And if it's an output, we'll go in this piece of logic. So if it's an input, what are we going to do? Well, we're essentially going to allocate some memory, some GPU memory using the CUDA malloc async, which is going to allocate our GPU memory. And we're going to put it at position, buffers of I, okay? So we're just populating that m buffers member variable, which is the vector of void pointers with the memory that we're allocating. So we specify where we're allocating it to and then the size, how much memory do we want to allocate. So the amount of memory we're going to allocate is, the number of channels that our input has times the height times the width. But for the batch size, what we're actually going to set it to is the maximum batch size, okay? And the reason for that is because we want to allocate the maximum possible amount of memory that might be used. And even if we end up using less later, that's okay. But since we're going to allocate it right now, we need to allocate the max possible that might be used later, which is going to be this max batch size. And then of course, the inputs are floats, so we need to allocate four bytes for each float. And then we specify the stream. And then we also save the dimensions because we're going to use these later in our actual inference method. So we're just going to save these m input dims. That's just a vector of dim3, so channel height width. So we're just going to save that for the inputs. And then if the binding is an output, very similar process, we essentially just, allocate memory depending on the size of the output. So output length float. Once again, max batch size, we're doing that again, size of float. And then we essentially save the length of the output as a float to this vector here. So this is just a vector of uint32. So we're going to save that later for when we're reading the outputs. And the reason in this loop here, so this loop we're just computing the size of the output. You might be wondering why do we start at index 1 instead of 0. It's because index 0 is the batch size, and we kind of want to ignore that because first of all, for dynamically batched models, that'll be -1, and for statically sized models, well, it'll already be specified by the max batch size variable. So we got it covered there. So, and then that's the end of this function here. So, once we're done that, we will synchronize our streams so that all the GPU, so that essentially, we wait for all the GPU operations to complete. And then after that, we will destroy our stream. So then let's go back to our main function here, our main file, pardon me. Okay. So now we're just going to do some preparation of the inputs here. So just for the sake of this example, we're gonna send for the input, we're gonna provide, when we run inference, we're gonna set the batch size of that equal to what the op batch size was set by the user up here. So if you set it 4, we're gonna set 4 inputs in parallel, a batch size of 4 to run inference on 4 inputs at once. Okay, and for our input image here, we'll use using facechip.jpg. which is already in the correct size for our arc face model. It's already 112 by 112 RGB. So that's perfect, but based on your own model, you'll need to either pre-process the image, appropriately using like a face detector and, a warp affinity method to get it down to the right size, or you can do like a static resize. You can just resize it. There's lots of ways to pre-process your image, but basically we're going to use OpenCV to read the image from disk, and then OpenCV natively reads in BGR. We need to convert to RGB, as that's what our model is expecting. So we're just going to do a color conversion here. We're now going to upload it to a GPU mat using the CUDA GPU mat upload method here. So now we have our image 112 by 112 chip in GPU memory. Now we're going to call this get input dims method on our engine instance, which basically returns the m input dimensions, which we saved earlier, if you remember that. So this is basically, you probably don't need to do this in your code, but I'm just doing it so that we can dynamically populate some inputs which are of the correct size. So in this case, the vector only has one element, because for our model we only have a single input, the input being dynamic batch size by 3 channels by 112 by 112, but there of course could be models with multiple inputs, so this vector could have more items in it. And then we define a vector of vectors of GPU mats to actually hold all of our inputs, which we're eventually going to be passing to inference here. Okay, and just something I should mention while we're talking about this, because this looks pretty confusing, a vector of vectors of GPU mats. Why do we have a vector of vector? Essentially for this reason here. So the expected input format is the input, the batch, and then the image. Okay, so let's say you have two inputs. So then this outer vector represents the inputs, this inner vector represents the batch, and then this is actually the images themselves, so the actual each input. Hopefully that makes sense. I know it sounds kind of confusing, but I'm hoping that, just looking at the code makes it a little more confusing. So it makes it a little more clear, pardon me. So we're going to iterate over each input that we have in our model. Once again, we only have one input, so this loop only iterates once. And then now we iterate over our batch size. So our batch size is 4, so this loop is going to iterate 4 times. And then basically here it's telling you, hey, if you need to resize your input using scaling or padding or whatever, you should probably do that right now, because otherwise, TensorRT is not going to be happy if you provide an input that's not of the correct size. Although our code does have checking internally to check that the provided inputs are correct, this is probably where you want to do the resizing. So, here we're just going to do a resize, which is not something I actually recommend, because, when you just call purely resize, it's going to you don't necessarily maintain the aspect ratio, and that's not something we want. But our image is already 112 by 112, so it's not going to make a difference, because we're taking a 112 by 112 image and resizing it to 112 by 112 again, so no difference is had. But in case, I have provided this method here, utility method, which is resize keep aspect ratio. So for example, you could use this method to resize to new size while maintaining the aspect ratio. So this will basically add letterbox padding to make sure that the aspect ratio is maintained. So for example, if using like a retina face or an SCRFD or YOLO model, which requires a fixed input size, generally 640 by 640 or 1280 by 1280, then you generally want to use a function like this, where you resize it but maintain the aspect ratio by adding a letterbox padding. So you can choose to do that if you want, and then basically we add it to the input here, and then we add outside that loop, we add it to this inputs here. So by the end, when we are done all these loops, we have this vector of vectors of GPU mats. So this outer vector just has size 1, inner one has size 4, and then we have our 4 CV GPU mats in there. So hopefully it makes sense now. Now we're going to define our pre-processing code. Okay. By default, the run inference method. So let's have a look at that. So here you will see that for the run inference method, let me move this aside a little, we have these default subvals and div vals and normalize set to true. Okay, and what is the meaning behind that? So basically what happens is that using all those default configurations there, the input values are going to get normalized between 0 and 1 point f, okay? So if you remember currently, basically, you know, our inputs are currently as uint8_t. So the max is 255, but it's basically needs to get converted to float, and then most models require some sort of normalization, okay? So if you set this normalize flag to false, then it's basically going to leave it as in the range of 0 to 255. But if you set it to true like we have, like our model expects, then it's going to normalize it to between 0 and 1. And now something else that we're also going to specify is we're going to specify the sub vals and the div vals for each channel to 0.5. And basically what that does is it takes these values here, and then first it subtracts 0.5. Okay, so now your range is negative 0.5 to 0.5, and then it divides that by 0.5 for each channel. So now your range is negative 1 to 1. So that's just the format that our model is expecting in this case. And a lot of trained models do expect that format, so that's why we have this code here. And now we're going to start running inference. So I'll just, before we jump into like the actual inference code, which is probably the most interesting part, we will just finish what's in this main file because we're almost done. You know, for our benchmarks here, we discard the first inference time just to warm things up, you know, make sure all the weights are loaded, caching is hot, everything's good, and then we're just going to benchmark 100 iterations, you know, timing before, and once it finishes, print out the benchmark, how long it took. So what's the average time per inference? You know, you have to remember to divide by the batch size as well, total numeration, which is here, the inputs of 0. And then finally, we just print the feature vectors. So the format of the outputs is a little different than the inputs. So the output could be considered even more confusing because it's a triple vector, triple nested vector of vectors of float. And basically what the output is unlike the input, the output is batch output feature vector. So this code here demonstrates how you can iterate over the output. So the outermost loop is our batch. Then the second loop is going to be our actual output. So in our case, you know, this outer loop is going to iterate 4 times because we have a input batch of 4, so the output batch is also going to be 4. The second loop is going to iterate for each output. So we only have one output for our model, but if your model has more outputs, you know, this loop would iterate more times. And then finally, we're just printing the actual feature vector. So in our case, it prints a feature vector of length 512 floats. However, we just print the first 10 elements because, we don't want to congest your terminal with, you know, a bunch of feature vectors here. All right, so let's actually dive into the run inference method now. Okay. Run inference. All right, what is happening here? What is happening? So the first thing we do, I'm not going to dive into this part, but basically it's just a bunch of error checking, you know, make sure that the input vector is not empty, make sure that the second nested vector is not empty, you know, make sure that the input size, you know, matches with how many inputs is our model expecting, which once again, we consult this variable here, which we defined earlier in the load network method, or that we populated, pardon me, in the load network method. You know, we're also checking, does support batch size. If it does, you know, you obviously can only provide a batch size of 1 if it does not support batch sizing. And then the next thing we're going to do is we're going to save the batch size. So this is the actual batch size. So there was like the op batch size and max batch size, but this is the batch size based on what's the batch size that the user actually provided for this particular call to run inference. So that's going to be the size of this nested vector, okay, because we're going to be using this later. And then we're doing some other error checking, you know, obviously the batch size needs to be constant for every input if you have a multi-input model, because otherwise that won't make sense. And then here, we're going to create a CUDA stream. This CUDA stream is going to be used all through this like inference code all the way to the end. So it's going to be quite useful, and then we're going to destroy it right at the end there. So we're going to do everything asynchronously in the code here. So the first thing we need to do is we need to pre-process all of our inputs. Okay, and how we're going to do that is we're essentially going to iterate over every input for every batch size, and then we do a little more error checking. And then this is where we do the first interesting thing. So previously, the input dimension of our model, if we had a dynamic batch size model, this would have been -1. The batch size would have been -1 for the model. So now we're actually populating it with the actual batch size for this call to run inference. For example, this call to run inference, the batch size might be 1, but then the subsequent time it might be 4, then it might be 8, then it might be back to 1, then 2. That's why we need to define it for every call to run inference, since we do support dynamic batch sizes in that way. And then we actually set the binding dimension. So yeah, basically for that input, we're basically setting this now input dimension that we've fully defined here. Okay, so we're going to do this for every input that we have. The next thing we're going to do is we're essentially going to do a kind of like a color channel conversion, basically converting from NHWC to NCHW. Now, what the heck is the difference between these two? Because I always get confused. So let's look here. Let's go to handy dandy Google and open up my favorite image. So when you read an image from OpenCV, it is going to have NHWC format. And what that means is that essentially we have a value from the red channel, then the green channel, then the blue channel, red, green, blue, RGB, 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 and so on for the entire image. And that's how the pixels are going to be grouped. That is not the format that TensorRT expects. TensorRT expects NCHW. And what that means is that we need all the values from the first channel, from the R channel, then all the values from the green channel, then all the values from the blue channel. So we basically need to do that conversion appropriately. So let's go back to our code here, and that's essentially what we're doing in this section here. So we essentially, extract out each channel, and then we split them, and we do a little culmination there. And then this is where we're actually applying the normalization code that I spoke to before. So, if we did specify normalization, then not only do we convert the uint32 uint8 underscore t to a float value, a 32-bit float, but we also divide it by 255 just to normalize it to the range of 0 to 1. Whereas if you did not specify normalization, we leave it as is. And now we apply the actual, we do the subtraction and the division. So, if we use the values that were defined in our main file here, so of 0.5 for each of the channels, then this code, by the end of it, we're going to have values in the range of -1 to 1. So each one of our floats is going to be in that range. Now, essentially what we're doing is that we're taking a pointer to our data, and then we're actually, so this data is already in GPU memory, if you remember, because we uploaded it to GPU memory a while ago, actually in our main function, and all the preprocessing, we're using CUDA GPU method. So it's already in GPU memory, so then we can just do a CUDA memcopy async. We're going from device to device, and essentially we're copying this data to the buffer that we pre-allocated in the M buffers, okay? And we do this for each input. So as you can see, this for loop here, we're iterating for each input. So in our case, we just have one input, but if you have multiple inputs, it's going to appropriately set the data in our vector of void pointers for which we've pre-allocated the memory right here. And if you remember, we allocated enough memory for the input for the max batch size, whereas here, we might not necessarily need to use all that memory, but at least we know that there is enough memory, and we're not going to do some sort of like buffer overflow. So that's good here. So we're going to do that for each one of our inputs. We don't need to worry about synchronizing the stream because we can do that right at the end. So we've done that. Now we check that all input dimensions have been specified. If you don't have this called here, then this call further down here will fail. But since we did actually set the binding dimension for all of the inputs, then we should be covered there. So we should have no error here. And then now that we've specified all the inputs in our M buffers, and we've also allocated memory for the outputs in our M buffers, we can actually run inference in QV2, that is asynchronous inference. So basically we just pass the mbuffers vector, which has the allocated memory and the actual inputs for our inputs and the allocated memory for our outputs. We can pass just the same inference CUDA stream that we've been using above here in our asynchronous memcopy, and then we can proceed. So now we're going to copy the outputs. Okay, so essentially for the outputs, what we're going to do, as you can remember, the outer vector was going to contain our batch, and then the second vector was going to contain our actual output, and then the final vector is the feature vector itself. So that's why we iterate over the loops in this format. And then basically we're going to get the output length. And what's going on here? Output length float of output binding minus the num inputs. Output binding. Oh, this is just to off. I see what's happening here. Okay. Yeah, so the reason, so in this loop here, the reason we don't start at 0, the reason we start at num inputs is kind of like as the offset, because we're going to be using this index to access m buffers, and of course we need to like skip over a few since m buffers also contains our inputs. So we want the first one to be the index of our output, which is why here then we need to, when accessing, you know, elements of this vector here, we need to subtract the inputs just to normalize this, so that on the first iteration of the loop, this is actually, this evaluates to 0. So that's what we want there. And then basically, you know, we'll take our output, we'll resize it with the appropriate size, and then we will finally do a asynchronous memcopy where we copy the output from the buffer into this output variable. Okay. So into, yeah, output.data. And essentially what we're doing here is we're just doing some pointer arithmetics to make sure that we get the correct output there, and, you know, we account for batch and all this fun stuff. I won't dive into that, but you can trust that it works. And basically just something to be mindful of is that now we're copying from device, so from GPU back to CPU memory, because this output variable is in CPU memory. Because, you know, now that we have a feature vector, we probably want to do some CPU operations on it. You know, with face recognition feature vectors, you generally do cosine similarity. You could do that with GPU memory, but in our case, we'll just do CPU memory just to keep it simple. So we copy it to that, and then we move it finally to this vector of vectors. And then at the end of this loop, we add it to our feature vectors, which is essentially the output of this method, which was passed by reference here. Okay, so we've done that. And then finally, you know, once that loop's done, we've copied all the outputs asynchronously. Finally, we can synchronize our CUDA stream. So this will be blocking until all these operations above are finished. And once they're done, this method will return, hopefully, you know, a successful error code, and then we can destroy our stream. And that is the end of it. And yeah, and then we finish the run inference method. So, you know, that happens internally every time we call run inference, and it's relatively fast. So yeah, I mean, this code is particularly powerful just because it does work with models of single, multiple inputs, single or multiple outputs, you know, variable batch sizes. The one thing it currently does not work with is models which have dynamic input height and width for the inputs. That is something I am going to work on in the future, but I haven't had time to implement quite yet. But yeah, I think that covers most of it. You know, I hope you found this tutorial helpful. You know, if you have any questions, feel free to either leave a comment with your question or open up an issue on this GitHub repository, and I'll try my best to get back to you. And yeah, if you found this tutorial or video helpful, I would really appreciate if you could go on to my repository here and leave a star. You know, that just helps more people have access to it. And yeah, that's it. I hope you guys have a good day. Good luck coding.